This is version 2 of effect size from chapter 11. The first version was wrong. There were some problems with the formulas. So I fixed it on April 23rd, and this is posted, let's see, it's going to be posted about 8 o'clock or so on the 23rd. So if you've watched this slideshow previously and didn't hear all this, that was the wrong one. This is the correct one. All right, so again, and you get done with this slideshow, you should be able to calculate effect size using Cohen's d. Cohen's d is a way to measure this thing that we call effect size. Effect size, you could think of it as really the difference between the two sample means. Right? For example, if I have a treatment that I think is going to help students on the SAT, I might randomly assign 20 students to one of two groups of my experiment. One takes my sample class and then takes the SAT. The other one is a control group, just takes the SAT. The effect size would be the difference between the two groups. It would be the amount of increase or decrease that my special course causes. And I would expect that it's going to increase the SAT scores for these kids by comparing the experimental group, who gets the practice SAT course, with the control group. Right? I can estimate the improvement that the average student will see after doing my class. That's the effect size. Essentially, this concept of effect size, what Cohen's d does is quantify the size of the difference between the two groups. We can take this effect size and turn it into a number and talk about how much improvement is due to my SAT class, or how much better did students do in 2020 compared to 2019. The effect size is an important concept because it's a good way to judge the practical significance of the results. When we do hypothesis testing, we're looking at the statistical significance of the results. And many people get caught up in that word significance. When we find that something is statistically significant, it doesn't mean it's important. It means it's kind of special. It means that it has a probability of occurring due to chance alone less than the level of significance. So if alpha is 0.05, right, and we say something is statistically significant, what we're saying is that effect is going to occur less than 5 times in 100 due to chance. People misinterpret that word significance to mean importance, and they tend to judge the value of their results depending upon the results of the statistical test. Remember, we make the decision by whether the outcome, the t we calculate, is in the rejection region, and whether that t obtained is just over the top, just inside the rejection region, or way out in the tail, is not an indication of the effect size. People misinterpret that. That's just the probability of the result. Remember, the probability of the result can be affected by n. N increases the power of an experiment, makes it more likely to find something if it really exists. Well, that can kind of distort how people think about the importance of the results. So by focusing on Cohen's d and effect size, we can think of the practical significance of the results. All right, how much does the statistical significance really impact the performance of individuals? One way to look at it is the absolute or raw difference between two group means. Right? That's the absolute effect size. So if the kids who take my SAT class score 1,500 on average, and the kids who do not take the SAT class score 1,000 on average, my absolute effect size would be 500 SAT points. Cohen's d, sorry, I'm not sure why it's making that annoying chime. Cohen's d is a standardized difference between two groups. What standardized means is it judges the absolute difference against some criterion. And as we'll see, that criterion is the standard deviation. This is what we did with the z-score, if you remember way back when. We looked at the difference of an individual from the sample mean, told us how far that person was from the sample mean in terms of whatever the dependent variable was. And then we divided by the standard deviation, which is the typical difference from the sample mean. So we could look to see if that person was above or below the typical difference. Now it's important to remember with Cohen's d and thinking about effect size that it matters only when we reject the null hypothesis, because it's when we reject the null hypothesis that we are saying we have evidence of something. We have found an effect. Therefore, we can take the next step and say, how large is the effect? If we fail to reject the null hypothesis, we're saying there's nothing there. And there's nothing there, there's nothing there. There's no effect to judge how large it may be. So we only have to worry about Cohen's d when we reject the null hypothesis. Cohen's d can be calculated for pretty much any statistical test, and in general, Cohen said it should be the mean of the population, the difference between the population means. So he conceived it as if we reject the null hypothesis, you're saying the populations are really different. So you look at the difference between the two population means and divide by a standard deviation. Now, when we do a t-test, we're estimating the mean of the populations with the mean of the samples. So we're going to look at the difference between the samples. Cohen also gave us some sense of how to interpret this ratio. And he says if the effect size is a 0.2, it should be considered a small effect. 0.8 would be a large effect. Anything in the middle would be a medium effect. And that's an important thing to consider. He gives us how to judge it. Just because something's statistically significant doesn't mean it is going to be meaningful. For example, consider my SAT example. Had a raw effect size of 500 points. When calculating Cohen's d, I might find the effect size is 0.10, which Cohen would say is a small effect. And that should be considered when instituting the treatment, right? Consider what my treatment might cost. Kids have to put extra time in it, takes time away from school and sports and family. It might cost a lot of money. It might be labor intensive. We might have 6 or 7 tutors per child, and they have to spend 3 hours a day on this course, right? So you might say, for all of that effort, is it worth a small effect size? Just because it's statistically significant doesn't necessarily mean that it's something that is really meaningful in the long run or something worthwhile in the long run. For the independent samples t-test, Cohen's d is calculated in this way. The mean for group 1 minus the mean for group 2 divided by the pooled standard deviation. Now this is where I went off the rails in the last slideshow. The pooled standard deviation is the square root of the pooled variance. Right? We're accustomed, I'll go with purple today, right? We're accustomed to the pooled variance. That's part of what we need for the denominator of the independent samples t-test. If you take the square root of that variance, you have the pooled standard deviation. And it is that standard deviation, the square root, that is the denominator of the Cohen's d formula. Now this is relatively easy to find. These are things we're going to have laying around after we've done a hypothesis test. we're certainly going to have the sample means, and we're going to have the pooled variance, s squared sub p. So what we're going to do is take the square root of one of those numbers, and we are off to the races. As an example, this is the example from the previous lecture for independent samples t, where a future me compares my class students in my class, the averages for spring 2020 versus spring 2019 in Psych 100. So the data was for 12 and 15 students, right, their final course average. And there's the means, 83.5, 79.6, and then the sums of squares for each of those samples. When we did that hypothesis test, we rejected the null hypothesis. So this would be a situation in which I would be interested in Cohen's d. I see an absolute effect size of 3.9 points. That doesn't look very impressive, 3.9 points, but it's statistically significant. So we had evidence that students in the spring 2020 semester did better than in the spring 2019 semester. So let's look at Cohen's d for this data. First, remember the pooled variance. The pooled variance is sums of squares of 1 plus the sums of squares of the other group divided by the degrees of freedom. When we did this is what the calculations look like when we did the hypothesis test. And if you look back in that other example, if you copied it out, you should see this somewhere in your work. The pooled variance was 13.16. So to find Cohen's d, there's the formula for Cohen's d. I'm going to look back at the data from that problem, and there it is repeated, and I'm going to need the pooled variance, which is 13.16. So looking at Cohen's d, I need to find the pooled standard deviation. So I want to take the square root of the pooled variance. So there's the formula set up. So I take the square root of 13.16, and I get a nice 3.63. So there's the formula for Cohen's d, 83.5 minus 79.6 divided by 3.63. That's 3.9 over 3.63, which gives me a Cohen's d of 1.07. Now, according to Cohen's scale, that's greater than 0.8, so it should be considered a large effect size. Now, one thing to note here, right, I got a positive 1.07. If I had done this problem reversed with 2019 as group 1 in this formula and 2020 as group 2 for this formula, I would have a negative 1.07. When Cohen wants us to interpret the d, we ignore the sign. Look at the absolute value of the value. So whether it's negative 1.7 or 1.07, they're the same and would indicate a large effect size. Oh, by the way, this example was also discussed in the class questions from 423. The second example, the hours worked example, this is from the video, and there's a screenshot from the class on 421. This is the ending example from the lecture on 421. Now, we did reject the null hypothesis for this, and we had evidence that the younger employees worked significantly more than the older employees, and there's the data all carried forward. Since we rejected the null hypothesis, we should be concerned about Cohen's d. So once again, there's the formula, the difference between the two sample means divided by the pooled standard deviation. There's the data again with the pooled variance, and we have to turn that into a pooled standard deviation by taking the square root. So the square root of 0.98 is 0.99. I double checked that math. It's weird, but that's how it is. Because remember, the square root of 1 is 1. So as you get close to 1, there's not a huge difference. So the square root of 0.98 is 0.99. Putting that into the Cohen's d formula, there's the two sample means divided by 0.99. We have 4.7, which is the absolute effect size, 4.7 hours. divide that by 0.99, and we get a Cohen's d of 4.75, which we could call a very large effect size. That says that difference of 4.7 hours is impressive. It is a very large difference given the typical variability we see in hours worked. We can also talk about Cohen's d for dependent samples t-tests, and that's the topic for next week, but I thought I would introduce it here. Cohen's d equals d bar, the mean d, divided by the standard deviation of d. Now, this is going to get a little confusing because there's d's all over the place, and these d's are not all the same. This is Cohen's d, and when I talk about Cohen's d, I'm going to write Cohen in front of it. The d's that are over here, that d stands for a difference, and when we do a dependent samples t-test, we have to get the difference between two dependent variables, and we call that a lowercase d. So it might get a little confusing, but when we talk about this next week, mostly the d's that we're going to talk about are going to be these differences between observations. If it's Cohen's d, I'm going to write Cohen in front of it, so we'll all be on the same page. That's it. I apologize for that earlier mistake. Take care. Have a good weekend.